Well, good morning, everybody.
Morning.
Today is the first day of the rest of your life, right? We are, I've been telling you, right, that it gets better, right? It's going to get easier, and it is. You're gonna tell me, right, when we're done with this unit, oh, this was much better than the first two. It's still physics, right? It's still hard. It still takes work. And if I have one word of warning for you is, yeah, this is going to feel better. It's going to feel easier. And you might even get to that point where you go, I kind of get this. And then you'll be worried because, I've been training you to not get it the entire time, right? So don't stop doing what you're doing. If there is a time in this class to really hit a slam dunk, to really just get the material and get as good a score as you can on the next exam, this is it, right? This is really the time when you can offset any poor performance on the first two exams, which is normal. Like poor performance on the first two exams is like that, we expect that. This is the buffer. And it's not the buffer just because I'll softball it or anything. In fact, this is what I did my graduate work in. So you're gonna get a little bit more than might otherwise happen. But it is a breath of fresh air. Do you remember kinematics at all?
Yeah.
A little bit? Do you like kinematics now?
I love it.
Comparatively, right? This is kind of going to be like that feeling, right? It's not kinematics, it's light. It's going to be totally different in terms of the equations and the math and all. But it's that feeling of, I can do this. Why wasn't the rest of the course like this? And the answer is, the universe isn't always like this, right? But where so far we've done electric and magnetic fields can't be seen. We can measure them, we can do iron filings, but they are, it's very real, but the way we understand them is very abstracted in pictures and all that kind of stuff. With optics, we can see what's going on. Like right in front of us, we'll be able to make it happen, right? And so there's just this kind of connection to it that I really, really enjoy. Now, we are going to do chapter 24. However, we need to do something else. Where did it go? I know I put it in here somewhere, and it has not appeared. Because why would it? Did I put it? No. See, you have everything planned and ready to go the day before, and it comes and bites you in the rear end. Guaranteed going to happen. Where did it go? This is the punishment. This is what I get for being ahead. See? This is just what happens. Come on, bring it up. Just got to get the file in the right spot. Got it there. Through the magic of the cloud. Like I said, through the magic of the cloud. I'm going to have to do this the old-fashioned way. Yeah, cloud says it's there. Aha.
Yay.
It took the hamsters a little while. They're on daylight savings time also. And so they've been having a rough time of it. One of the great tragedies, I think, of the modern physics curriculum is that we don't have enough time to tell you the story that's going on behind the scenes. It's just math and plug this in and do that, and it robs science of a very important factor, which is the human factor, and the people and events and things that happened. I let you in on it a little bit here and there, but I am going to take about 20 minutes right now to give you background and context. And these are good stories, okay? They're true stories, but they're good stories about the people involved, because I'm actually setting up the rest of the semester. What I'm going to talk about right now is going to carry us all the way through to the end. We're going to end up in quantum mechanics and nuclear physics because of the story I'm going to tell you right now. Now, I am not a history teacher. If I wasn't allowed to teach science, I would teach history, just because I just think history is stories and I love stories. You are not required to know any dates. I will never ask you a date of what something happened, but I do expect you to kind of know who's who and what they did. And I'll try really hard to tell you as we go along. But you want to connect name with what they did to move science forward, because the story I'm going to tell you actually isn't about light. It happens to have light in it, but it's not the story of light. It's the story of modern science as we know it, okay? So we're going to ask just a few easy, basic questions. How do you make light? What do you do?
Photons. Oh, you press a light switch?
Yeah, you press a light switch, right? Okay, so basic, Mr. Balogh, right? Okay. Do you realize that 50 years ago that wasn't as simple a thing? Right? Seriously, sometimes it wouldn't work, right? Okay. And prior to electrification, how did you make light?
Lit a candle.
You burnt something, okay, right? You had to catch it on fire, right? And really, we could argue, right, that a light bulb, right, or the sun, or a campfire, they're basically all doing the same thing, right? Burn something, okay? Somebody said once that it all went wrong when we got fire from the gods, and I think that's pretty close, right? It's kind of the end of human civilization. We know it started right there, right? So, because nowadays, we can put the sun into a bomb, right? And deliver it places. Like we've done so much with our science that it both harms and benefits, right? But in a very simple sort of idea, creating light is straightforward. Burn something, heat it up enough so that it glows, and you will get this thing that we call light. And as you're about to find out, there's way more to it than that. Just a lot more to it. But I said we're going to start with simple questions, right? Okay. How fast does it go? Yeah, C is the answer, right? Lowercase c, right, is the symbol for the speed of light. And it is a number. 2.9, yeah, 8, 7, something. We need to get the whole thing. 2.9979. 2458. I can't remember all those numbers. 99792458. Did I get that?
Yes.
Okay. 299,792,458 meters per second. We usually, since this is a pain to put in the calculator, right, is we just do 3 times 10 to the 8. Okay? That's going to be close enough for a majority of our calculations to be just fine. So we know how fast it goes. I wish I had the next half hour literally to tell you this story, because it's really a fascinating one. Because we started thinking that light was infinite. Like it just was there all the time and it didn't have a time travel. And then we discovered through just amazing scientific making so many mistakes and finally getting to the right answer, we finally converged on that. But I don't have time for that question, because there's a better question. This is the question that's going to take us for the rest of the semester. Actually, you didn't know this, but we've already been starting to answer this question already. And it's such a simple question, isn't it? Like really, it's 3 words. But in the same like spirit of, well, Newton's second law, it's only got 3 things in it. How bad could it be? This question is going to take us through the end of the semester to answer. Spoiler alert, we're still not quite sure. We have some pretty good ideas, but we're still working on it, okay? We finally got what is mass 12 years ago. But, all right, so in an effort to answer the question, I want to give you kind of the who's who of history in terms of science that weighed in on this very important question. Like, what is this thing that we call light? And because this is physics, we're going to start with Isaac Newton. He wasn't the first, of course, right? I think ever since we evolved organs to pick up electromagnetic waves, we've probably been trying to answer a similar question, right? So, but we'll start with, because physics really, modern physics starts with Isaac Newton. We'll start with Isaac Newton. Isaac Newton, he did a lot of stuff. Most of it wasn't physics. But he published really 2 major works that are scientifically relevant for physics. First one was the Principia, which has all the laws of motion. We dealt with that one in Physics 2a. This other one is optics. Okay, he was writing in Latin because that was the cool language to write in the age, right? And but in this like multiple 100-page manuscript, Newton is laying out the basic idea of the nature of light, how you can capture it, how you can focus it, and do all these other things. Again, it's one of those sort of incredible works that sort of summarizes everything. You can see there's like a drawing of a prism and an eyeball, like, Newton's really getting into it. And Newton developed a theory, an explanation for all of the optical phenomenon that we see. Like, why does a prism break up things into a rainbow? How do eyeballs focus light? Why, if you put a lens together, 2 lenses in a telescope, they'll let you see something far away, right? He's trying to answer all of these questions and more. And he develops this idea, and he coins a term. It's the corpuscular nature of light. Now, those of you that are into any kind of biology, anatomy, physiology, you know what a corpuscle is, right? Maybe? Don't remember that one? In its Latin roots, it means chunk of, okay? I know it's got a more modern medical application, but like it's just a little unit of. And so Newton proposes what is really the first concrete description of what light is, and that it is a particle. It consists of little individual corpuscles, or little tiny chunks of light, that interact with materials in ways. And he has lots of justifications for this. Like, he's like, if you take a look at a shadow from like a single light source, and again, Newton's working long before light bulbs, right? So all he's got is like candles and torches and fires, right? And so he says, look, you get sharp shadows. We're kind of not used to sharp shadows today. I haven't gone crazy. I felt like going back to the Dark Ages today, but this is for demonstration purposes. But like, do you see the shadow of my hand on the wall? Do you see how that's a very sharp shadow there? Sharp shadows come from singular light sources, right? In our modern age, we have so much light around us all the time that all of our shadows go soft, right? You look at your shadow on the desk and you see that it's not very sharp because it's got multiple light directions coming from all over the place, and so it kind of diffuses the shadow out. But Newton argued that because of that sharpness, the particles of light were getting blocked, and if it were, say, a wave, it should be able to bend around an object, and thus the shadows would be all blurry. And he's got all these other ideas, but Newton comes down on the side of light. Look, light's a particle, right? It's like tennis balls or something, right? When something burns, it's throwing off these particles of light. Now, what happens when Newton comes out and says something scientific? Yeah, this is like the gospel truth, isn't it? This is like the scientific equivalent of Moses wandering off the mountain and going, hey, there's 10 things I think we should look at, right? Like it's the law, right? This is Newton. He described the entire universe in 4 laws, and now he comes out and says, light's a particle? Sir, yes, sir, right? Like, if Newton said it, it had to be the case, right? And so more than 50 to 70 years goes by with Newton's theory and opinion being the way it is, right? This is, Newton said it, Newton's a genius, therefore that must be the way that it is. But every good story needs a young whippersnapper, pun intended, in order to come along and sort of upset the status quo, right? Now, Thomas Young is working after the death of Newton, so at least Newton's died and only his ghost can come back to haunt him. But Thomas Young, as a young scientist and physicist in the early part of the 1800s, like 1802, 1803, is doing some experiments with light. Now, this is an experiment we are going to get into in detail later, okay? And I don't expect you to understand anything about it right now. He does several experiments, one of which is this 2-slit experiment, the double slit experiment, where he takes a light source. He didn't have light bulbs either, right? But nowadays we would use a light bulb or a laser, okay? Shines the light on 2 closely spaced slits and looks at the pattern that appears on the screen. As we will learn together later, 3 chapters from now, the pattern that Thomas Young sees on the screen can only come from one thing. It's called an interference pattern, and it can only be produced by waves. We kind of back up just a little bit. We go back to Physics 2a when we did waves and sound. Okay? There were 4 things that waves, called the wave phenomenon. They were reflection, refraction, diffraction, and interference. We are about to do all 4 of those again. Okay? We're actually going to dedicate a chapter to each of them. Actually, diffraction and interference is the last chapter. They kind of go together. Okay? But we're going to dedicate an entire chapter in the unit to each of these 4 wave phenomenon. And you may not remember, maybe you weren't taught it, but in my class, I tried to get my students to remember, of the 4, reflection, refraction, diffraction, interference, 2 of those can be copied by particles. Like particles can do them also. Does anybody remember what the 2 were?
Deflection.
It's the first 2. It's the ones that start with R. Okay? The 2 that start with the same letter are the ones that particles can do. So particles can reflect, right? If I grab a particle, right, and I slam that particle into a change in medium, right, it'll bounce off. That's a reflection. Well, waves do that too. The sound waves bounce off the walls and come back to your ears and all that kind of stuff. Refraction we'll get into later, but particles do it too. But diffraction and interference are unique to waves. Particles cannot diffract and they cannot interfere with each other. And it's not like bouncing off each other, that's just reflection. Interference is overlapping at the same place at the same time. Constructive and destructive. When we did sound waves, we could cancel sound waves out or make them louder. So Thomas Young is doing this experiment. He gets an interference pattern, and interference can only come from what kind of thing? A wave. What's Thomas Young's problem now? He has evidence that Newton is wrong. right? Like evidence, like science, okay? And so, what do? You've got the evidence, but everybody's saying Newton said it is a particle. So what do? You go on TikTok and make a thing and try to get it go viral. This is 1801. So Thomas Young is finishing up his research, right? He's going to present it a year following, right? But he goes for the jugular. Okay? Yeah. This is science talk this is real smack right here, right? Okay? Look at the words, right? So does he admit that he respects Newton? He's using this word venerate, right? That's an old-timey fancy word for I really respect, right? And acknowledge the work that Newton did, okay? But he can be wrong? Infallible means to be wrong, okay? Right? He's liable to err, old-timey words, that perhaps sometimes he has even retarded. It's a slur today, but what does it mean?
To slow down.
It means to slow down, right? So what's Young saying here?
Look, I respect the guy, but that doesn't mean I don't think he wasn't right.
He wasn't right. And not only do I think he wasn't right, but he slowed down scientific progress. It's as close as a scientist gets to calling somebody out, right? Okay, right? So, Thomas Young goes to an international conference. At that time, Paris, France, was the center of all things international worldwide science, at least in the European parts of the world. And he goes to a conference and he starts presenting his material at this conference. And you need to understand, conferences are basically just a whole bunch of lectures, right? Scientists never leave school, and so we are comfortable at our conferences just lecturing each other, right? And so Young is standing up in this lecture hall, and there's about 200 of the world's best scientists in the room, right? Experts in their fields. He's the young guy in the room. Like he hasn't really established himself. And what does he do? He stands up and starts telling them that Newton was wrong. How do you think this goes over? This is bad, right? Okay. But as gentlemen of science, sorry ladies, you weren't allowed in yet. We're working on that still. There's an understanding that you don't interrupt the speaker, no matter how you might feel about what they're saying. We are scientists after all, we're composed, all this kind of stuff. Well, for one scientist, it was too much. Simeon Poisson, who was a respected scientist in Paris, right, known in his field, which was optics. And by the way, whose last name means fish. This has nothing to do with the story, but I just think it's hilarious. So he stands up in the middle of Thomas Young's lecture, clears his throat. Room. And starts to tell Young how wrong he is. Everybody's like, this doesn't happen. What is going on here? And Young begins to say, well, I have the experimental evidence this is what I'm presenting here. And they start going back and forth, okay? And they can't come to, and this, like I said, this is unheard of. There's been a breach of etiquette and protocol here, right? But Thomas Young isn't going to call Poisson out on that. It's too much of a gentleman. So they start kind of, and so what do two educated and well-meaning men in the early 19th century do when they have an argument that can't be resolved with logic? A duel.
Yeah.
I told you this story was going to be good, right? Okay? So right there, I'm bending the truth just slightly here. Right there, they're smart. They're not going to go out in the street and shoot each other, okay, or get swords or anything like that. But they agree right there to a contest of dueling experiments. Because this is science, right? We should, and so people are questioning Thomas Young's methodology and like how did he collimate his light? There's a bunch of little details in there, right? But you don't need to know. But like there's some questions surrounding Young's method. And so Poisson posits or puts forth an explanation. This is Poisson's explanation. Poisson, remember, does not believe that light is a wave. He believes light. He believes in Newton. He light's a particle. He's like, okay, look, if you are right, Thomas Young, then we should be able to take and this is greatly enlarged, but we should be able to take a small, like, spherical object. We'll make it metal so that the light can bounce off of it, all kind of stuff, right? And if light diffracts, which Poisson did not believe in, okay, he said diffraction would cause the rays to bend around the small metal object. In the shadow that is cast by the object, right, if the rays are diffracting and bending around the object, they should meet in the shadow, and there should be a little dot of light where light shouldn't be. I, Simeon Poisson, do not believe that this is the case. Thomas Young says, you're on, Mr. He didn't say it that way. But like he said, okay, let's do it. So they like, the conference stopped. Like the conference erupted, like, and nobody could do anything. People just started going home. And it took several weeks, but they finally kind of drew up this framework for a contest, and there was like a money prize. Like it got a big deal, okay? And so it was really, I didn't put his name in there. It's really Simeon Poisson that, Augustin Fresnel. You don't need to know his name. But if you've ever heard of Fresnel lenses or anything like that, it's that same Fresnel. And who really starts championing Thomas Young's sort of side of the story, because Thomas Young needs somebody with a little bit more experience maybe, or that's been respected as a scientist. And so they do the experiment, and guess what they find?
Does it do that?
It doesn't. I'll show you later when we get to diffraction, okay? But they turn off the lights, they turn on the single light source, they put a little tiny sphere in the beam, and what appears in the shadow? A dot. To this day, that dot is called Poisson's dot. Okay? Not because scientists are jerks, okay? But because Simeon Poisson was the first to put forth or posit what would later become the correct explanation for what is happening. Belief is not a requirement in science, okay? There are many scientists who believe lots of things, and you need it as a human being to really kind of give you hope and drive to go and investigate and learn about things. But belief is not a requirement for the truth. Not in science, not when you're asking scientific questions. And so even though Poisson didn't believe this was going to happen, he used correct physics to explain what ultimately experimentally would be verified. And so that's why it's called Poisson's spot to this day. And this blew the lid off of the light question. Because up till now, Newton, light's a particle, that's all it can be. And here Thomas Young and Poisson come along and just blow the lid off of that. And really what happens in the early 1800s is this division of the physics community into two camps. There were those who said, no, something else is going on here. It can't possibly be a wave. Light's got to be a particle. Newton was right. And then the other side that's like, no, well, look, there's evidence right here. So the main sort of point of the particle group, the particle camp, okay, which, by the way, was the majority, like a big majority, like 80% of the scientific community. There is a singular problem that cannot be explained with wave mechanics that light does. It comes from the sun. And what's between the sun and the earth? A vacuum. And waves can't travel in vacuums. Right? You need a medium. Right? You need a medium for light to travel in. And so where's the medium? Right? Like if the vacuum is empty space. So it can't possibly be a wave. It's doing something that's wave-like, but it can't possibly be a wave because it's coming from the sun. So this was like a major, major problem. And so what did the wave camp do? They invented something, right? To explain how waves could travel in a vacuum. And what they developed was an idea called the luminiferous ether. In case you haven't ever heard of the luminiferous ether, let me explain it to you, okay? The luminiferous ether is the medium in which light travels through the universe. You can't see it. You can't touch it. You can't taste it. But it has to be there. Light's a wave, and it needs a medium in which to travel. Ergo, the ether must exist. Does this sound like anything scientific you've heard in the last 2 decades? Dark matter. Dark matter is a solution to a problem. What's the problem?
Light or waves.
Astronomers have measured the mass density of the universe and discovered that approximately 95% of our universe is missing. Like if you go out and you do a statistical average of all the galaxies and stuff, blah, 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 you find that what you see represents only about 5% of the mass that's actually in the universe. So where's the other 95%? It's got to be dark. What's dark matter? I don't know. Can't see it, can't touch it, can't taste it, but it must be there. I'm not denigrating these ideas because they sound silly. As a scientist and as an experimental scientist, not a theorist, right? I'm on the experimental side. An idea, a hypothesis, a belief doesn't have any scientific legs unless there's a way to test what's going on. With dark matter, we're looking for it. We've got some hints that we can actually detect dark matter particles. There's some scientists that think we've actually done that yet, and we're still waiting for more detections to really nail down what's going on. But there are ways to detect dark matter particles, and based on the beliefs and theories and ideas of theorists, right? And so experimentalists are out looking for them. And it was no different for the luminiferous ether. They came up with ways to test, right, what's going on. And so for from about the early 1800s all the way to the early 1900s, so almost a period of 100 years, scientists were looking for the luminiferous ether. Technology advances, right? And the story goes on. And we can attribute this to several individuals, but I'm not going to require you to know their names. But let's just suffice it to say, pictures happen, right? We finally get this ability to capture photos onto glass plates and later onto plastic plates and later onto SD cards in our phones, right? But this new technology that allows us to capture an instant of time, right, and freeze it, and really look at what's going on, gives rise to a very interesting phenomenon. This is what happens when you try to take a picture of something, but you only let a very tiny amount of light into the camera. Can you tell what it is? It is a face. Humans are really good at recognizing faces, which is why I picked this example, right? But more importantly, is it a complete face? No. What do you see? Dots. If light were a wave, the wave should contain all of the information that it came of the object that it came from. And so therefore, if you let a little tiny bit of light into the camera shutter, it should be a very, very faint, but in completely entire picture because the wave contains all the information. But it doesn't, right? We have a physical device, right? Now, some of you are smart and you're saying, they're going, well, Mr. Balogh, that's chemicals, right? Because photographic film was all about getting sodium, silver ions or whatever to react to light. And so, the chemicals are molecules, molecules are dots. This works for digital sensors as well, okay? Here's what happens when you let more light through. The issue is that you're not getting all of the information at low light exposures, okay? At low light exposures, you are very definitely getting dots, right? And when you get enough of them, it looks like a complete picture, okay? But it doesn't take away from the fact that your picture was made up of what? Particles. There's the digital version down there on the bottom. Okay, not a face, but just like letting little bits of light through onto a sensor. Okay. The pendulum has swung the other way, hasn't it? Okay, right? The wave people have experimental evidence, and now the light people have experimental evidence, right? And Newton on their side, right? Like this is a good situation to be in. I don't have time to tell you stories. I'm going to do it anyway. You need to understand something about scientific progress and making mistakes and how, and I'm going to use this word very deliberately, how seductive an idea can be. I was in my senior level electricity and magnetism class. This is an entire 2 semesters where we go through the first 2 units of what you guys have just done. So imagine the first 2 units, but spread out to 2 semesters, no hand holding, horrible mathematics, all kinds of good stuff going on, right? Okay. Dr. Spencer was my teacher, and Dr. Spencer was a teacher who would come into the room and he would start his lecture over here. It was a room almost like this one in that there were chalkboards on every wall, okay? And he would start over here, and he would start deriving and explaining and mathing, and he would get to this wall, and he'd keep going, right? And and then he'd get to that wall, and then he'd start working his way around the back, right? And if he got back to the same board he started on, he'd just start erasing and writing at the same time as he went, okay? And it was a job of, well, we better keep up. And we would rate classes on number of circuits around the room that Dr. Spencer would complete, right? Somebody missed a class. Oh man, you missed a three around the room class. You're dead, right? Okay. Today was only 1 around the room. It was nice, right? Like that was the thing. So we were in like oh, it was bad, and it was glorious, and it was hard, and and one day Dr. Spencer comes in, he walks through the door, and he walks to the front. So already we know something is different. He stands up there and he says, "Today, I'm going to prove to you that the ether exists." Spoiler alert, it doesn't. We know this, okay? And he says, and we're like, "Oh, Dr. Spencer, no, we know this story. Don't bother." He's like, "No, I'm going to prove to you the ether exists." He started right there. He ended right about here. I still remember this like it was yesterday. Somewhere around here, we believed. Like it was the most beautiful thing we have ever seen. It explained everything. It worked, and it didn't require very many bad integrals. And we had been doing bad integrals, right? It was simple. It was elegant. It predicted things. It was seductive, right? Because it was able to do everything, and it did it simply, and it was amazing, and we wanted more of that. Anything to save us from what we were going through, right? Got to here, and he stopped, and he looked at it. He was about 20 minutes into class, 50-minute class. And he looked at it, and he's like, "Yeah, that's it. Too bad it's not true." Put his chalk on the board and walked out. In the age before mic drops, that was the most significant mic drop I had ever seen in my entire life. He left a room of about 21 students absolutely devastated. What was the lesson?
Don't believe everything you hear.
Just because it's beautiful doesn't necessarily mean it's true. In science, in physics particularly, beauty can be like equated to like mathematical elegance. Right? Right, it makes sense, it's easy, all that kind of stuff, right? And on the next class, our hands were in the air. We're like, well, we know that the field lines are a lie, and we still use those. Why can't we use this? And he's like, because the field lines are based on something real. Ether theory has no reality to it. Zero. Just because something sounds good doesn't mean it's right. This is where chapter 24 starts. Okay? That's all a prelude and a context for what we're about to learn. And we're going to come back to this. Okay? We're going to come back to this because we're missing some kind of famous scientists, aren't we? Can anybody think of anything that we've missed in terms of like famous scientists that changed our understanding of the universe? Einstein, okay, right? James Clerk Maxwell was the Einstein of the 1800s. Like seriously, like direct link between those, okay? Matter of fact, it would be Maxwell that would inspire Einstein to go on and do the work that he did. They never met each other. Einstein was born in the same year that Maxwell died. A fitting relay, hand the baton off if I've ever seen one, okay? But like, what you are looking at, I don't expect you to understand. It's not about understanding. You are looking at Maxwell's equations. James Clerk Maxwell took everything that was known about electricity and magnetism, and in the 1850s, gave mathematical rigor to Michael Faraday's work. And in one of the best team-ups of history, the experimentalist Michael Faraday teamed up with the theoretician James Clerk Maxwell and came up with our best description of what light is. You are looking at 4 equations that tell you everything you need to know about electricity and magnetism. I've given them to you in their what I consider their most natural form. It's a differential calculus form, and you don't have that math. Unless you've been taking really bad calculus classes, you might recognize the divergence and curl, the upside down delta. But don't worry about any of that. Don't worry about any of that. I believe it is one of my life's missions to make sure every student that passes through my classes are exposed to these. Because what these are is going to blow your mind. It's all right here, but you can play with Maxwell's equations and get something incredible out of them. Everybody get your calculators out. We're going to go straight to the punchline because you guys don't want to see a whole bunch of derivatives. What did I do? What did I do with my pen? Yeah, I never keep track. Okay. Maxwell, so having summarized all electricity and magnetism and correcting a couple of problems, which is really what his genius was, then started playing with them and something fell out. It was, curiously, a speed of an electric and magnetic field that had been coupled together through Faraday's law of electromagnetic induction. And that speed turned out to be 1 over the square root of mu naught times epsilon naught. Okay, so do you remember what mu naught is? Like, not its number, but like what it is. Like what's the dead giveaway when mu naught's there? Magnetic field is present somewhere, somehow, right? Okay. So this velocity is involved. It has something to do with the magnetic field. Okay. What's this? It's the same version, but for the electric field, right? So with these two constants here, electric and magnetic field are definitely involved. Okay. Mu naught. Everybody do this, and Brandon, shut up. It's all right. You just fast. Okay. This is 4 pi times 10 to the minus 7. And epsilon naught is 8.85 times 10 to the minus 12. Okay? Good luck getting all the parentheses correct and all that kind of stuff, right? Okay? But in the interest of time, while you type that out, we're going to let Brandon tell us, because he already said it, what this is.
It's C.
What's the number?
It's 299,792,458. If you use the actual constants.
What has James Clerk Maxwell discovered?
The speed of light.
From theory. Experimentally, this speed had been known for a while.
Yeah.
But now, James Clerk Maxwell has discovered light. What is light? You know you've made it when your equations end up on a t-shirt. Right? Okay. James Clerk Maxwell has discovered a wave in the electromagnetic field. A sine and cosine type function that self-propagates, that requires no medium other than an electric and magnetic field. Because we know from Faraday's law of electromagnetic induction that if you change a magnetic field strength, you change the flux, what do you get? A changing magnetic flux produces a circulation of the electric field, and electric fields couple and produce magnetic fields. And so what you get is a wave that self-propagates, requires no medium other than the fields themselves, and so can exist in the vacuum of space, and it travels at the speed that light travels. What is light? It's everything. Do any of you like Wi-Fi? Like, without Wi-Fi, you can't get the things, right? That's light. Can you see the light waves coming off of the access point? No, because our sensors, our eyeballs, are tuned to only see the visible wavelength. Do you see how tiny the visible portion of the electromagnetic spectrum is? Maxwell has discovered them all. Not just the ones that we can see with our Mark I eyeballs, but all of them. He has discovered what will become cell phones, right? And X-rays and everything. What do you see when you see these?
Everything. 42.
It looks like bad math. It is. It's actually pretty elegant in its own right. But to me, as one who has been trained in this science, I see it gets me emotional, sorry. I see a reason or an explanation for why the sky is blue. We're going to learn why the sky is blue. In these equations is an explanation for why that paint looks gray and that paint looks white, and why your shirt is green. In these equations is a description of every electrical circuit that has ever existed. In these equations, I can tell you why milk and clouds are white, why the colors of the rainbow are the way they are, how DVDs and Blu-rays are able to store information optically, for why venous blood is purple and arterial blood is red, and how to make the internet work. 4 equations, just 4. And we can explain pretty much all of modern science. This is what physics is after. This is what physicists would call simple. Okay? This is elegance. It doesn't require an infinite number of equations. You really only need 4. And then you can get everything else. That took longer than it should have, but I had too much fun. Maxwell's equations give us this wave in the electric and magnetic field. These waves propagate through the field. And I want to show you a video so that you can get a mental model of what this wave looks like. With no sound for some reason. Here we go. Give me a second. You can skip all of the bad calculus.
So suppose that there can be a wave in the intensity of the electric field.
So that's electric field, waving.
It's a transverse plane wave, and it travels, of course, at the speed of light. But consider the field at any one instant. Since it's up in circulation about this path.
We just studied a lot of loops, didn't we?
According to Faraday's law, that means that there must be magnetic flux through that same path, and furthermore, that it must be changing in time. And that can only mean one thing. A magnetic wave must tag along with the electric wave everywhere it goes.
Do you see how it's 3D? And at right angles to each other?
But, and here's the crux of the problem, that in turn means at any instant there's a circulation of the magnetic field about this path. And according to Ampere's law, that can only be true if there's current flowing through it. But in empty space,
Maxwell fixed that problem. Ampere's law was incomplete. We haven't taught you about Ampere's law. You don't need to worry about it. But this wave, right, travels, well, wiggles in 2 dimensions, right? So like if the electric field is coming up and down like this and it's sort of coming straight at you, what's the magnetic field doing?
Perpendicular.
Same thing, but so if the electric field's in the y-axis, right? If we kind of say, well, electric field is going up and down, then what does the magnetic field need to be doing? It needs to be going left and right. Okay?
Oh, yes, it's white.
Darned Maxwell. Darned Maxwell. There we go. I did the wrong input. Which way is this wave traveling? If it's wiggling up and down and left and right, did you catch in the video which way it was going? Yeah, in or out. Okay. Again, magnetic fields, electric fields, we can't help but do 3D, right? Okay. So this wave is either going in or out of the screen. It travels perpendicular to both the electric and magnetic fields. And it can be it's really a hard picture to draw. Do I even attempt it? So there's my axes. Here's my wave propagation direction. And the electric field is kind of doing this. And the magnetic field is doing... You see how hard this is? Yeah, it was terrible. Okay, right? But like, that's the idea. There's better pictures on the internet of this going on, okay? This leads to this. When we apply all that wave theory that we learned in 2A to these electric and magnetic sines and cosines, these wiggly bits, right? We get relationships that same relationships we got from physics 2A. Does anybody vaguely remember that one? Speed of a wave is equal to its wavelength times its frequency, where wavelength is like the distance between 2 peaks, right? Okay, frequency is how many peaks pass by a certain amount of time. Well, when it comes to light, we know the speed, right? And so the entire spectrum can be all the frequencies that correspond to all the wavelengths. Let's just do the visible section. Roy G. Biv. Who was Roy G. Biv? No idea, okay? But it stands for red, orange, yellow, green, blue, indigo, violet. The order of the colors of the rainbow. Don't let me start on what indigo is. Hello. My name is Inigo Montoya. You killed my father. Prepare to die. I'm glad some of you knew what that reference was. I did have one year where the entire class looked at me like I was insane.
I would have walked out.
No, I signed homework. You will go watch. You will go watch The Princess Bride. Yeah. And thank me. All right. So let's see. Reds correspond to what we call we don't use low. We use short wavelengths. No, I did that backwards.
Yeah.
Long wavelengths. Thank you. Come back, pen. Where'd my pen go? There it goes. Long wavelengths, okay? Blues, indigos, and violets are the short wavelengths. So for blue lights and violet lights, the peaks are really close together. And for red light, they're really spread out. Frequency, remember this equation over here is all about what wavelength and frequency are doing. It's the relationship between wavelength and frequency, not speed and frequency. Because the speed of a wave depends on only one thing. Former students, you forget this one?
Wait, say it again.
Speed of a wave depends only on one thing. What is it? The medium in which it travels. And that's true for light as well. The speed of light does change depending on what medium it's in. It changes when it goes into water or glass or anything else, right? But it's set by the properties of the medium. So therefore, if frequency goes up, what changes?
The wavelength.
The wavelength, not the speed, right? So wavelength and frequency are inverses of each other. So if the wavelength is long or big, stretched out, is the frequency high or low? It's low. And vice versa. So we often refer to blue light as high frequency, short wavelength light. We usually don't say both. We usually just say one or the other. We either say it's high frequency or we say it's short wavelength. Red light, on the other hand, right? Opposites. The entire spectrum is like this. Okay? The visible portion is this tiny, tiny part. Okay? The rest of the diagram isn't really to scale. This one sort of is, right? Where you see, like, do you see how big infrared is compared to visible? Yeah. You see how big ultraviolet is compared again to visible, right? Visible is a tiny, tiny portion of the entire amount of the electromagnetic spectrum, okay? And so going further into the reds, where we can't see them with our eyes, we get the infrareds. And then the radio waves, okay? And the radio waves just make up the balance of all of the long wavelength radiation, okay? So this is where your, wireless, your cell phone's wireless, all that kind of stuff is coming from the radio. But what is radio? What are radio waves? They are light waves. So from now on, when this physicist says light, I mean it. I don't mean just what we can see. What's light? Every electromagnetic wave, regardless of whether we can see it with our eyes or not. What speed do radio waves travel at? One answer, it's the speed of light. Because why? Because they're light waves. What speed do gamma rays travel at? Speed of light. They all are light waves. Light usually means what we can see with our eyes. But in physics, it's any electromagnetic wave. We call it electromagnetic radiation. We try not to use the R word too often. Makes people worried. Because there's a difference between electromagnetic radiation and ionizing radiation. Do you guys ever hear that if you use your cell phone next to your ear, you're going to get cancer or something like that? Right? It's bumpkiss, okay? But that was a line that somebody drew, an idiot drew between, ionizing radiation causes cancer, so therefore electromagnetic radiation must cause cancer. Doesn't. Okay? So you gotta be careful. Ultraviolet going up, so these are shorter wavelength, higher frequencies. And then you've probably heard of X-rays. X-rays can be bad, they can give you cancer, but they can be good. We don't have to cut you open to see what's wrong. Right? It's always a balance, okay? Gamma rays. Gamma rays take up the sort of the rest. So like radio on one end for forever, gamma on the other end, just high energy electromagnetic radiation, and then these zones in between. The energy. Let me just throw some equations at you you're going to need to use in your homework. Okay? The energy that a electromagnetic wave carries, okay, can be found if you know how strong your electric field is, or if you know how strong your magnetic field is. This is potential energy, capital U, so it has units of joules. When you throw in epsilon naught, whatever units it's in, an electric field in its standard units, newtons per coulomb or volts per meter, doesn't matter, you will get joules out. Same thing goes for the magnetic field. Goes in Teslas, and whatever the units of mu naught are, it'll come out in joules. You can just take that to the bank. Pretty easy calculation. The magnitudes of the electric and magnetic fields in an electromagnetic wave are related by the speed of light, which is kind of fun. And then there's one more thing I've got to show you, and it's the reason I brought this. Okay? Because light is a wave, and that wave wiggles, we can cause the wiggle to happen in only certain directions. This is called a polarizer. Okay? It's a piece of plastic that's got something called a polarizer in it. And you'll notice that the first thing that happens when I introduce the polarizer, what happens to the intensity of the light? It went down, right? Okay? In fact, if we took careful measurements, we'd find that 50% of the light has been cut. Okay? This is a second polarizer. If I put the second polarizer on there, we don't see that much happens. Okay? It's certainly not another 50% drop-off. Okay? There's a little tiny amount of drop-off, but that's called attenuation because the light is scattering as it moves through the plastic. Okay? Now watch this.
What?
Science. The first polarizer took the light and forced it to wiggle in one direction. Think of it like, so normal light is what we call unpolarized. The electric field doesn't always come at you along the y-axis. It can be rotated into an infinite number of directions, right? But the magnetic field will always be 90 degrees to it. But unpolarized light is a mixture of every rotation around that direction that the wave is traveling. What the polarizer does is it forces it to go in only one direction. So if I say that this is horizontally polarized now, okay, and I take another horizontal polarizer, nothing happens, right? Horizontal is horizontal. But how much of a horizontal wave can travel through a vertical fence? None. The first one has forced the light to only be horizontal. The second one only lets vertically polarized light through. So the result is 0. This feature of polarizers is captured in an equation, a statement called Malis's law, I think is what it's called. Okay, those S's are intensities. This is what your book uses. I prefer this one because intensity to me is spelled with an I. You can do whatever you want. Okay. There's a historical reason for using the S. It's something called the pointing vector that you don't need to worry about. But basically, this equation right here, it's the same in both boxes, gives you the intensity of light after it passes through two polarizers. I naught would be the intensity that the light's coming through the first polarizer. Okay? And then the second intensity depends on the angle at which the polarizer is put, right? Okay? So what happens if the angle is 90 degrees? What's the cosine of 90? 0, right? And 0 squared is still 0, right? But we can find any other intensity we want based on that angle. Why would we want to control light like that?
Sunglasses.
Oh, you've heard of polarized sunglasses?
Yes.
Yeah? Can you guys see the computer screen?
No. Oh. Yeah.
Sort of. Right? Okay. How does the computer produce all the different colors and brightnesses? It's using a polarizer. Polarizers made it possible for us to take monitors from being this thick to being this thin. What are these?
3D glasses.
These are 3D glasses. Did anybody go to 3D movies anymore?
Not really.
Yeah, not really. Right? Okay. Anybody that's ever been to a 3D movie knows that if you take the glasses off and look at the screen, what do you see?
Blue and red.
Blurry, right? It's not blue and red
Oh, not anymore.
because blue and red would be a black and white movie. In color, you have to separate two images. Your eyes need to see two different images to be able to pull off the illusion of three dimensions. So how do you get, say, this eye to see one image and this eye to see a separate but offset image?
Could you have them at like
Polarize the pictures. The two projectors are producing two different polarized pictures so that the one that's vertically polarized, say, enters this eye, and the one that's horizontal enters this eye. Your eyes see two different images like they normally do when they're attached to your brain, okay? And so it begins to reinterpret the 3D. How do you test to see if the sunglasses you're being sold are in fact polarized? Sunglass Hut in the mall is telling you a story, you're not sure. What do?
Oh.
Right? You line up, take two pairs of identical sunglasses, turn them at 90 degrees to each other. And what will happen? They'll block the light if they're polarized. If they're not, it won't happen.
What did you call that in the beginning of class? Like where the shadow.
Magic.
No, right? The shadow was right up against the wall.
Oh, sharp shadow? Yeah, the defined edge to a shadow, that kind of stuff, right? Polarizers make it possible for us to do things like thin monitors, but also eliminate glare. Like if we're looking out, it's kind of hard to see, but there's some cars out there in that parking lot. Is there anything really glary out here? You guys know what glare looks like? It's that really bright reflection that comes off of water or something like that, okay? I've got a picture. I've got time to show you. Let me show you this. This is an awful picture, okay? I know because I took it, okay? And I'm saying it's awful not because I took it, but because I on purpose made it bad. This picture has a lot of glare in it. Can anybody tell what the object is? It's a tree stump on the beach. It's a piece of driftwood on the beach, okay? And so you see kind of the beach, the sand there in the background, but basically this picture is really bad because the glare is causing problems. So this is what my camera saw naturally as I took the picture. Here's the picture when I added a glass polarizer onto the front of my camera lens.
Whoa. What?
Polarizers can knock out that glare because glare is horizontally polarized light. The next time you see a reflection off of like the chrome of a car or the sunlight in the back window of a car that just kind of hits you and you go, ah, right? If you're wearing polarized sunglasses, that glare gets knocked out. If you're wearing polarized sunglasses, don't do this while you're driving. Tilt your head and you'll see the glare come back.
What?
Okay? Because it's horizontally polarized light that our eyes are sensitive to. That's why we go, it's glary. Okay? So these two pictures I did not take, but you can see in the top picture how there's no definition to the sky because the light's unpolarized, but once it passes through the physical polarizing filter on a camera lens, like a real camera, not a cell phone camera, they'll look like this. Okay? They attach to the front. Okay? And you can rotate the polarizer to get whatever glare out that you need. Modern cameras kind of do this, but they use it with machine learning and stuff like that to try and fake it. I want to be here, mostly because there's no people in this picture. But do you see how the ocean and the sky are kind of like, I don't know, blah? Same picture, but with a polarizer, right? Do you see how all of a sudden you can kind of see more into the water? And look at the sky. Look at the clouds in the sky, right? Do you see how this blue, the kind of whitish sky turns into a more blue sky, right? This is the power of polarization and being able to knock out glare and do other tricks, right? All based on Maxwell's equations and our understanding that light is a wave. We will spend the next 3.5 weeks coming to grips with the wave-like nature of light before we return to Albert Einstein, who's got a different idea. I'll see you Thursday. Have a great rest of the day.